Look up at the night sky, and what do you see? A sprinkle of stars, maybe a familiar constellation, but behind that seemingly serene canvas lies a universe teeming with secrets so bizarre they defy everything we think we know. Out there, hidden in the endless dark, are cosmic structures so vast, so strange, they rewrite the rules of reality itself. Imagine something so massive it makes galaxies look like specks of dust, or so dense it warps the very fabric of space and time. These aren't science fiction, they're real, and they're waiting to be uncovered. For centuries, we've mapped the heavens, charting planets and stars, convinced we were getting closer to understanding it all. But the universe loves a good plot twist. Just when we think we've got it figured out, it throws another enigma our way, structures so perplexing, even our sharpest minds can't fully explain them. Some stretch billions of light years across, like cosmic fingerprints left by forces we can't comprehend. Others glow with energies that shouldn't exist, whispering clues about dimensions beyond our own. What are they? How do they work? And most thrilling of all, what do they reveal about the true nature of reality? That's the journey we're embarking on today, a voyage to the edge of understanding where the known universe gives way to sheer wonder. We'll unravel 25 of the most mind-bending cosmic structures ever discovered, each one a mystery that challenges physics, defies logic, and humbles even the brightest scientists. From colossal walls of galaxies that shouldn't exist to voids so empty they feel like cosmic errors, these are the puzzles that keep astronomers awake at night. So buckle up, by the time we're done, you'll never look at the night sky the same way again. Deep in the far reaches of space, hidden behind the thick veil of stars and dust that make up our own Milky Way, lurks something colossal, something with a gravitational grip so strong it bends the motion of entire galaxies toward it. This is the Great Attractor, a cosmic enigma so powerful yet so elusive. Scientists have spent decades trying to unravel its secrets. Picture the entire Milky Way, along with thousands of other galaxies, being pulled toward an invisible point in the universe like a cosmic river flowing toward a waterfall. That's the Great Attractor's influence at work, but here's the twist: we can't see it directly. It sits in a region astronomers call the zone of avoidance, an area obscured by the dense clouds of gas, dust, and stars in our own galaxy's plane. It's like trying to spot a distant lighthouse through a thick fog. Even our most advanced telescopes struggle to pierce through this celestial curtain. Yet, by studying the bizarre movement of galaxies around it, we've deduced something massive must be there. Something with the gravitational pull of tens of thousands of Milky Ways combined. What could it be? Some suggest it's an enormous concentration of dark matter, an invisible scaffold shaping the cosmos. Others think it might be a supercluster of galaxies so densely packed, its gravity warps space on an unimaginable scale. But here's where it gets even stranger. Recent observations hint that the Great Attractor itself might just be a small part of an even larger structure, something called the Laniakea supercluster. That means this mysterious force tugging at galaxies might be one piece of a much grander cosmic web, a mere ripple in the vast gravitational ocean of the universe. So why does it matter? Because the Great Attractor challenges everything we thought we knew about the distribution of matter in the cosmos. If something this massive can stay hidden in plain sight, what else is out there lurking just beyond our view? Every discovery peels back another layer, revealing just how little we truly understand about the forces shaping our universe, and that's what makes it one of the greatest cosmic mysteries of our time. Now imagine a place in the universe so empty, so utterly devoid of matter, that if you were floating at its center, you'd see almost nothing in every direction for hundreds of millions of light years. This isn't science fiction, it's the Boots Void, one of the most baffling cosmic structures ever discovered. Stretching an incomprehensible 330 million light years across, this vast spherical region contains only a handful of galaxies. To put that in perspective, if our Milky Way were placed inside it, our nearest galactic neighbor would be so far away, its light would take tens of millions of years just to reach us. The Boots void defies everything we know about how the universe should be structured. According to cosmological models, matter should be distributed relatively evenly across the cosmos, with galaxies clustered like cities connected by highways of dark matter. But the Boots void is the equivalent of finding a desert the size of a continent where there should be bustling metropolises. There's barely a shack. Astronomers call it the Great Nothing, a cosmic oversight so glaring it makes them question whether they've fundamentally misunderstood the universe's architecture. What could create such a void? One theory suggests it might be the result of multiple smaller voids merging over billions of years, like soap bubbles combining into one enormous empty space. Another, more unsettling idea is that something invisible, perhaps an exotic form of dark energy, actively pushed matter out of this region, leaving behind an unnatural vacancy. And then there's the most tantalizing question of all: is it truly empty? Some researchers speculate that the void might be hiding rogue black holes, elusive dark matter structures, or even parallel universes pressing against our own like phantom fingerprints on the cosmic glass. The few galaxies that do exist inside the Boots void only deepen the mystery. Why are they there? Are they survivors of some ancient cosmic catastrophe, or do they hold clues about the void's formation? Each one is a lonely outpost in an otherwise barren expanse, challenging us to rethink how emptiness shapes the universe. The Boots void doesn't just defy expectations, it forces us to confront how much we still don't understand about the spaces between everything. And that's what makes it one of the universe's most profound puzzles. What if everything we thought we knew about the size and structure of the universe was just a fraction of the truth? That's the question staring back at us when we confront the Hercules-Corona Borealis Great Wall, a structure so vast it redefines the word colossal. Stretching an almost unimaginable 10 billion light-years across, this cosmic behemoth isn't just the largest known structure in the observable universe. It's a fundamental challenge to one of astronomy's most sacred principles, the cosmological principle. That principle states that, on a large enough scale, the universe should look roughly the same no matter where you are. Matter should be evenly distributed, like frosting spread smoothly across a cake. But the Hercules-Corona Borealis Great Wall, it's less like frosting and more like a gargantuan mountain range cutting through the cosmos, a glaring exception to the rule. Discovered in 2013 by mapping gamma-ray bursts, the brightest explosions in the universe, this structure isn't just big, it's impossibly big. To grasp its scale, imagine a single thread in a spider's web, but that thread is longer than a third of the entire observable universe. If you could travel at the speed of light, it would take you 10 billion years just to go from one end to the other. And yet, according to our current understanding, nothing should be able to grow that large in the time since the Big Bang. The universe simply hasn't existed long enough for gravity to pull matter into such an enormous structure. So how did it form? One theory suggests it might be a fossil, a remnant of the universe's earliest moments, when quantum fluctuations left behind dense patches of matter that ballooned into these incomprehensible walls during cosmic inflation. Others speculate that unknown forces, perhaps tied to dark energy or exotic physics, played a role in sculpting it. But here's the real kicker. If structures like this exist, it implies the universe might be far more uneven, far more lumpy than we ever predicted. That doesn't just tweak our models, it threatens to upend them entirely. And then there's the haunting possibility that the Hercules-Corona Borealis Great Wall isn't alone. Could there be even larger structures lurking beyond the edges of what we can observe? Each discovery peels back another layer of the universe's secrets, revealing a cosmos far stranger, far more mysterious than we ever dared to imagine. This isn't just a wall of galaxies, it's a boundary to our understanding. daring us to rethink everything. Rising from the heart of our galaxy like two colossal hourglasses of pure energy, the Fermi Bubbles stretch 25,000 light-years into space, one erupting above the Milky Way's disk, the other plunging below it. These twin towers of gamma rays, discovered by the Fermi Gamma Ray Space Telescope in 2010, glow with the fury of a million suns, yet their origins remain one of astrophysics' most tantalizing puzzles. Imagine two vast spheres of ultra-hot gas, each pumping out enough high-energy radiation to outshine the rest of the galaxy combined, and you're still only scratching the surface of their mystery. What could unleash such titanic structures? One leading theory points to our galaxy's supermassive black hole, Sagittarius, a star. Astronomers suspect that 6 million years ago, this sleeping giant might have awakened in a violent feeding frenzy, devouring nearby stars and gas with such ferocity that it spewed jets of energy straight through the galactic poles. These jets, erupting at nearly the speed of light, could have inflated the bubbles like cosmic balloons, leaving behind these lingering shockwaves of radiation. But here's the twist: the bubble's edges are razor-sharp, as if sculpted by some unseen force. That crisp boundary defies expectations, suggesting whatever created them wasn't just powerful, it was precise. Then there's the dark matter angle. Some scientists propose that the bubbles might be the aftermath of countless dark matter particles colliding and annihilating each other near the galaxy's core, releasing bursts of gamma rays in the process. It's a provocative idea, one that could turn these bubbles into the first visible signature of dark matter's hidden interactions. But if that's true, why don't other galaxies show similar structures? The Milky Way might be hiding a secret recipe for cosmic fireworks that others lack. And just when the puzzle seems complex enough, the bubbles throw another curveball. They're filled with fast-moving cosmic rays, particles accelerated to energies that dwarf anything our most powerful colliders can produce. How? No one knows for sure. The more we study these gargantuan structures, the more questions they ignite. They stand as silent monuments to some cataclysmic event, or perhaps an ongoing process hidden in plain sight, reminding us that even our home galaxy holds enigmas too big to ignore. The Fermi Bubbles aren't just a spectacle, they're a cosmic crime scene, and we're still piecing together what happened. Somewhere in the afterglow of the Big Bang, embedded in the faint whisper of radiation that fills the cosmos, lies a chilling anomaly, a patch of sky so inexplicably cold it might just rewrite the rules of reality. This is the cold spot in the cosmic microwave background, a cosmic bruise spanning nearly 2 billion light-years where the temperature dips mysteriously lower than anywhere else in the universe. Think of the CMB as the universe's baby picture, a snapshot of its infancy, but this particular corner of that photo is wrong. The temperature difference is subtle, just a few millionths of a degree, but in the ultra-precise world of cosmology, it screams that something extraordinary happened here. So what could leave such a mark? One hypothesis, the most mind-bending of all, suggests this might be a collision scar, not between galaxies or black holes, but between universes. Some theorists propose the cold spot could be evidence of our cosmos brushing against another bubble universe in the vast multiverse, a cosmic kiss that siphoned energy away and left this eerie cold patch behind. Picture two soap bubbles nudging each other in a sink, their surfaces warping at the point of contact. If true, this would be humanity's first tangible glimpse beyond the edges of our own reality. But not everyone's convinced. Skeptics argue the cold spot might be the footprint of a cosmic texture, a defect in the fabric of space-time left over from the universe's violent birth. These theoretical kinks in reality, like wrinkles in a crumpled bedsheet, could have unraveled and released energy, creating a void that appears colder than its surroundings. Others insist it's just a statistical fluke, a random fluctuation in the CMB, no more meaningful than finding an unusually shaped cloud in the sky. After all, if you roll the dice enough times, even the unlikeliest outcome will eventually appear. Yet the cold spot refuses to be explained away so easily. Recent studies reveal another layer of strangeness. It's surrounded by an unusual concentration of galaxies, as if space itself is stretched thinner there, distorting our view of what lies beyond. This has led to even wilder speculation. Could it be a window into a region of space with fundamentally different physical laws? Or perhaps the shadow of a supervoid so vast, its absence of matter cools light passing through it like cosmic air conditioning? What makes the cold spot so thrilling and so frustrating is that each new observation deepens the mystery rather than solves it. It challenges us to question whether we're seeing a cosmic accident, a fingerprint of the multiverse, or something entirely beyond our current physics. In a universe that's supposed to be uniform, this anomaly stands as a defiant reminder. There's still so much we don't know, and that's what makes it one of the most tantalizing puzzles written into the very fabric of the cosmos. Imagine the entire cosmos as a vast ocean with galaxies bobbing like boats on its surface. Now picture something strange. Many of those boats are all drifting in the same direction, as if pulled by an invisible current. That's the essence of the dark flow, one of the most unsettling mysteries in modern cosmology. Galaxy clusters, massive structures containing thousands of galaxies, aren't just expanding outward from the Big Bang as expected. They're also moving together, collectively streaming toward a single point beyond the edge of the observable universe. It's as if the universe itself is tipping its hand, hinting at something colossal lurking in the shadows. This bizarre motion was first detected in 2008 by studying the cosmic microwave background, the afterglow of the Big Bang. Astronomers noticed that hundreds of galaxy clusters were hurtling through space at breakneck speeds, up to 600 miles per second, all toward a region near the constellations Centaurus and Vela. At first, scientists assumed this was just a statistical fluke. But the more data they gathered, the clearer it became. This wasn't random. Something out there far beyond what our telescopes can see was exerting a gravitational tug so immense it was steering entire clusters like cosmic puppets on strings. So what could possibly be powerful enough to bend the motion of galaxies? One spine-tingling possibility is that the dark flow is evidence of another universe lurking beyond the boundaries of our own. In the multiverse theory, our cosmos might be just one bubble in an infinite froth of universes, each with its own physical laws. If a neighboring universe happened to brush against ours, its gravity could be leaking through, creating this eerie directional pull. It's like sensing the presence of a colossal ship just beyond the fog, invisible but undeniable. But not everyone's ready to jump to multiverse conclusions. Skeptics argue the dark flow might simply be a flaw in our measurements, a subtle error in how we interpret the motion of galaxy clusters. Others propose a less exotic but equally mind-bending explanation. A supermassive structure made of dark matter, stretching far into the unobservable universe, could be warping space-time on a scale we've never imagined. Picture a mountain range so vast, its foothills lie beyond the horizon, but its weight still shapes the rivers flowing toward it, the most unsettling part. If the dark flow is real, it means there's something bigger out there, something beyond the cosmic horizon we thought marked the limit of existence. That realization doesn't just challenge our models, it forces us to confront how small our observable universe might truly be. We're like goldfish in a pond, suddenly noticing the water's current and wondering what lies upstream. The dark flow isn't just a mystery, it's a cosmic wake-up call, reminding us that the universe still holds secrets we're only beginning to sense. Deep in the cosmic dark, where the first galaxies were still taking shape, float enormous ghosts of hydrogen-glowing behemoths so vast they could swallow entire galaxies whole. These are the Lyman alpha blobs, some of the most radiant and perplexing structures in the early universe. Picture a cosmic jellyfish, its tendrils stretching hundreds of thousands of light years, pulsing with a strange ultraviolet glow. That's what astronomers see when they point their telescopes at these ancient clouds, but what's causing them to shine so brightly remains one of astrophysics' greatest puzzles. Discovered in the late 1990s, these blobs get their name from the specific wavelength of light they emit. The Lyman alpha line, a fingerprint of hydrogen atoms being excited by some unseen energy source. But here's what baffles scientists. The amount of radiation pouring out of these structures is staggering, far more than what's emitted by even the most active galaxies inside them. It's like finding a neon sign in the desert, blazing with light but with no visible power source. So where's all this energy coming from? One leading theory points to newborn galaxies hidden within the blobs, their supermassive black holes and furious star formation heating the surrounding hydrogen like a cosmic furnace. Imagine a bustling city shrouded in fog. You can't see the buildings, but you know they're there from the glow of their streetlights. Similarly, these galaxies might be blasting out radiation that lights up the entire hydrogen cloud around them. But some blobs defy even this explanation, glowing too intensely for the galaxies inside them to be the sole culprits. That's led to wilder possibilities. Could these be the remnants of primordial gas collapsing under its own weight, forming the raw material for future galaxies? Or perhaps they're cosmic cauldrons where dark matter's invisible gravity is funneling gas into brilliant shock waves. There's even a chance they're illuminated by quasars so distant we can't see them, yet their light traveling for billions of years just to paint these hydrogen clouds with otherworldly radiance. What makes Lyman alpha blobs so extraordinary isn't just their size or luminosity, it's what they represent. These are time capsules from the universe's adolescence, snapshots of an era when galaxies were still assembling themselves. By studying them, we're peering into the cosmic nursery, watching as the first structures of the universe take shape. Yet with every answer they provide, they pose three more questions, reminding us that even the brightest objects in the cosmos can hide the darkest secrets. In a universe where chaos should reign supreme, where matter is supposedly scattered like dice thrown across a table, astronomers recently stumbled upon something that shouldn't exist, a colossal, near-perfect arc of galaxies so vast it rewrites the rules of cosmic structure. This is the giant arc, a staggering filament of galaxies and galaxy clusters stretching 3.3 billion light-years across the sky, a distance so immense it would take light from one end 33,000 times longer to reach the other than it has taken human civilization to rise from its earliest roots. At first glance, the giant arc appears almost artistic in its symmetry, a delicate crescent of light cutting through the darkness. But this isn't just a pretty arrangement, it's a direct challenge to one of cosmology's bedrock principles, the idea that, on the largest scales, the universe should look roughly the same in every direction. Instead, this structure defies expectations, its sheer size and striking shape suggesting that matter might be clumping together in ways our theories never predicted. Imagine shaking a rug to spread sand evenly across it, only to find the grains have inexplicably formed a perfect looping line. That's the level of bewilderment the giant arc has sparked among scientists. What makes it even stranger is its age. The giant arc isn't a modern phenomenon, it's ancient, dating back to a time when the universe was barely half its current age. For something this enormous to have formed so early, gravity would have needed to work at speeds that border on impossible, pulling galaxies into alignment like cosmic clockwork. Some researchers argue this might be evidence of exotic physics at play, perhaps dark matter interacting in ways we haven't accounted for, or relics of primordial energy fluctuations from the Big Bang itself. Others wonder if we're seeing the imprint of something even more profound, a fundamental flaw in how we model the universe's expansion, but the mystery deepens when you consider how we found it. Unlike other massive structures that reveal themselves through gravity's tug or the glow of clustered stars, the giant arc was spotted by mapping the positions of distant quasars' ultra-bright galactic cores powered by supermassive black holes. Their light, filtered through the ark's hydrogen gas, left telltale fingerprints in the data. It's like discovering the silhouette of a hidden mountain range by studying how it blocks the stars behind it. The giant arc doesn't just ask us to rethink the universe's architecture, it forces us to confront the limits of our own perception. If structures this colossal can hide in plain sight, what else might be lurking in the gaps between our observations? Every time we draw a new boundary for what's possible, the cosmos seems to laugh and redraw it in ways we never imagined. And that's what makes this arc more than just a curiosity. It's a cosmic provocation, daring us to question everything we thought we knew. Among the swirling chaos of the universe, where galaxies collide and stars are born in violent bursts, there exists a cosmic jewel so perfect it seems almost artificial: Hoag's object. This rare ring galaxy, floating some 600 million light-years away, defies expectations with its mesmerizing symmetry. A golden yellow core of ancient stars encircled by a pristine blue ring of youthful suns, separated by a near-perfect void of darkness. It's as if some celestial artist carefully painted a bullseye across the cosmos, and that's precisely what makes it so baffling. Most galaxies come in familiar shapes: spirals with winding arms, ellipticals like fuzzy orbs, or irregular blobs sculpted by collisions. But Hoag's object belongs to an elite class of less than 0.1% of known galaxies, where structure takes on an almost surreal precision. The ring isn't a loose collection of stars, it's a razor-sharp circle of star-forming regions, while the core remains eerily undisturbed, like a still pond inside a hurricane. How does something this balanced form in a universe ruled by chaos? One leading theory points to a long-ago galactic hit and run. Imagine a smaller galaxy plunging straight through the heart of a larger one, like a bullet through an apple. The gravitational shockwave could have sent stars and gas rippling outward, eventually settling into that breathtaking ring while leaving the core intact. It's a cosmic bullseye formed by a single, catastrophic shot. But there's a problem: Hoag's object shows no signs of the debris or distortion such an impact should leave behind. Where's the wreckage? Where's the trail of stars torn loose by the collision? It's as if the ring appeared by magic. That absence has given rise to another, even stranger idea: spontaneous instability. Some models suggest the ring might have formed from the galaxy's own internal turmoil, where rotating gas clouds became so dense they collapsed under their own gravity, igniting waves of star formation that propagated outward like ripples in a pond. In this scenario, Hoag's object isn't the product of a violent encounter but of a delicate, self-sustaining dance, a galaxy sculpting itself into perfection. Yet these theories only deepen the mystery, because if Hoag's object is so stable, so pristine, why aren't there more like it? The universe loves repeating patterns: spiral galaxies, elliptical galaxies, even the clumps of matter in the cosmic web. But ring galaxies like Hoag's are vanishingly rare, cosmic unicorns that appear once in a celestial blue moon. Perhaps they're fleeting, they're perfect rings destined to dissolve over eons as stars drift apart. Or maybe they're the survivors of a very specific, very improbable set of conditions, a recipe the universe seldom follows. What makes Hoag's object truly extraordinary isn't just its beauty, though. Nestled within its vast ring, astronomers have spotted another, smaller ring galaxy, a cosmic Russian doll, hinting that whatever process created this marvel might be more common than we thought, just hiding in plain sight. It's a reminder that the universe loves to surprise us, concealing its greatest puzzles behind layers of light and time. Hoag's object doesn't just challenge our understanding of galaxies, it whispers that there are still secrets written in the stars waiting to be deciphered. At the heart of a galaxy cluster so massive it bends the very fabric of space around it, lurks a monster unlike any other: the ultramassive black hole of the Phoenix cluster. This isn't just a supermassive black hole. It's a cosmic titan weighing in at a staggering 20 billion times the mass of our Sun. with an appetite so voracious it defies every model of how black holes should grow. But what makes this behemoth truly extraordinary isn't just its size, it's the sheer fury of its outbursts. Picture a black hole so powerful, its eruptions can sculpt entire galaxy clusters, heating gas across millions of light years and shutting down star formation on a cosmic scale. The Phoenix Cluster's black hole is a master of extremes. Its jets, twin spears of plasma launched at nearly the speed of light, stretch over 1.2 million light-years, making them some of the largest structures ever seen in the universe. These aren't gentle streams, they're galactic fire hoses, blasting through intergalactic space with enough energy to outshine every star in the Milky Way combined. Yet here's the paradox: black holes are supposed to be restrained by their own physics. The Eddington limit, a fundamental rule of astrophysics, states that a black hole's growth should slow as radiation pressure pushes back against infalling matter. But the Phoenix Cluster's black hole laughs in the face of this law, devouring gas and spewing energy at rates that should be impossible. It's like watching a candle produce the heat of a supernova. What's fueling this cosmic overachiever? The answer lies in the cluster's unique environment, a swirling ocean of superheated gas so dense, it funnels matter toward the black hole like water spiraling down a drain. Normally, black holes regulate their own growth by blowing away nearby gas with their radiation. But in the Phoenix Cluster, the gas is so plentiful and falls so relentlessly that even the black hole's most violent outbursts can't stop the feast. This creates a bizarre feedback loop. The more it eats, the more energy it releases, but the more energy it releases, the more it stirs up the surrounding gas, driving even more material into its grasp. It's a self-sustaining cycle of gluttony and fury. And then there's the black hole's most puzzling trick, its ability to toggle between states like a cosmic switch. Most black holes are either on, actively feeding and producing jets, or off, dormant and quiet. But this one flips between the two in geological instants, as if it can't decide whether to nap or unleash apocalypse. In just a few 100 million years, a blink in cosmic time, it has gone from dormant to hyperactive and back again, leaving astronomers scrambling to explain how something so massive can change its behavior so rapidly. The implications are profound. This black hole isn't just a passive occupant of its cluster, it's the architect shaping the destiny of hundreds of galaxies around it. Its outbursts heat the surrounding gas so intensely that they prevent it from cooling and forming new stars, a process called cluster-scale feedback. In essence, this single black hole holds the power to put an entire galaxy cluster into stasis, pressing pause on cosmic evolution itself. Yet for all its destructive power, the Phoenix Cluster's black hole might also be a creator. Some theorists suggest that when its jets eventually slow, the compressed gas in their wake could trigger waves of star formation, like seeds scattered by a wildfire. It's a reminder that even the most violent forces in the universe can have unintended consequences, cosmic chaos with a silver lining. What makes this black hole so captivating isn't just its record-breaking stats or its defiance of physics. It's the realization that even in the darkest corners of the cosmos, there are engines of transformation so powerful, they challenge our very understanding of how the universe grows, changes, and regulates itself. The Phoenix Cluster's black hole isn't just a curiosity. It's a cosmic lesson written in jets of plasma and waves of radiation, one we're only beginning to decipher. In the vast tapestry of cosmic phenomena, where chaos and asymmetry usually reign, the Red Rectangle Nebula stands out like a meticulously crafted puzzle, one that defies the very laws governing how stars die. Located about 2,300 light-years from Earth in the constellation Monoceros, this glowing geometric marvel isn't just another planetary nebula. It's a near-perfect rectangle of crimson light, bisected by an X-shaped spine of dust so precise, it looks as though it was sketched across the cosmos with a ruler and compass. And that's what makes it such a profound enigma. Dying stars aren't supposed to create structures this orderly. At the heart of the red rectangle lies a binary star system, two aging suns locked in a slow dance. As one of them shed its outer layers near the end of its life, it should have produced the typical chaotic glow of a planetary nebula, billowing clouds of gas expanding in all directions like a deflating balloon. Instead, we see this eerie symmetry, as if the star's death throes were filtered through some cosmic stencil. The leading theory suggests that the dense disk of dust and gas surrounding the binary stars acts like a nozzle, funneling ejected material into two opposing cones. From our vantage point, these cones overlap to form the illusion of a rectangle with its iconic X. But here's the catch: no model fully explains why the structure remains so razor-sharp, or why the dust lanes align with such geometric perfection. Then there's the mystery of its color, that deep, blood-red hue unlike any other nebula in the sky. The glow comes from a rare form of carbon-based molecules called polycyclic aromatic hydrocarbons, which fluoresce under ultraviolet light from the dying star. These molecules shouldn't survive this close to a star's intense radiation, yet here they thrive, painting the nebula in shades that baffle astrochemists. It's as if the red rectangle is playing by its own rules, rewriting the textbook on stellar chemistry in real time. Perhaps most tantalizing of all is the nebula's fleeting nature. In another few thousand years, a blink in cosmic time, the central stars will heat up, evaporating the dust disk and erasing the rectangle forever. What we're witnessing is a cosmic still life, a fleeting masterpiece that exists only because we're here at just the right moment to see it. That rarity raises a profound question. How many other stars die with this kind of precision, their final breath sculpted into shapes we've yet to imagine? The red rectangle doesn't just challenge our understanding of stellar death. It hints at an entire hidden gallery of celestial art waiting to be discovered. Just when astronomers thought they'd catalogued every type of cosmic structure, the universe unveiled another surprise: enormous rings of radio energy so perplexing, they've been dubbed odd radio circles. First detected in 2019 by Australia's ASCAP radio telescope, these ORCs loom like ghostly halos in the darkness, some spanning nearly 1 million light-years across. Picture a smoke ring blown by a giant, except this one could comfortably fit dozens of Milky Ways side by side. What makes these circles truly bizarre isn't just their size or symmetry, it's that they're completely invisible in every other wavelength of light. No stars, no gas, just eerie radio whispers from the void. Theories about their origins read like a cosmic detective's wildest brainstorming session. One leading idea suggests they're the aftermath of Titanic explosions, perhaps two supermassive black holes colliding in a catastrophic merger, sending shockwaves rippling through intergalactic space like ripples in a pond. These waves could accelerate electrons to near light speeds, creating the radio glow we detect. But there's a problem. No known black hole merger leaves such pristine circular remnants. The rings are too perfect, too undisturbed by the chaos around them. Then there's the space-time twist. Some astrophysicists speculate ORCs might be signatures of Einstein rings, gravitational mirages where massive objects warp space so severely they bend radio waves from distant galaxies into circular projections. It's like seeing a streetlight's reflection in a rain puddle, but on a cosmic scale. The catch: these rings appear in empty regions of space where there's no visible mass to create such distortions. Unless, of course, they're being made by something we can't see, clumps of dark matter so dense they act as invisible lenses. But the most tantalizing possibility is that ORCs represent something entirely new. Could they be the aftermath of never-before-seen dark matter interactions, or perhaps echoes from an ancient era when the universe's magnetic fields were far stronger, imprinting these structures like fossils in the cosmic record? Every observation deepens the puzzle. Recent studies reveal some ORCs contain galaxies at their centers, but not nearly massive enough to explain the ring's staggering energy. Others appear completely isolated, floating in the darkness with no apparent trigger. What makes these radio circles so revolutionary isn't just their mystery, it's how they challenge our observational limits. Before ASCAP ultra-sensitive arrays, we simply didn't have the technology to see them. That raises a humbling question. How many other enigmatic structures are hiding in plain sight, waiting for the right instruments to reveal them? The ORCs remind us that the universe still holds cards it hasn't played, and every new discovery peels back another layer of the unknown. Deep in the frigid outskirts of our solar system, far beyond the orbit of Neptune, drifts a tiny world with a mischievous name, the Goblin. This icy dwarf planet, officially designated 2015 TG387, earned its nickname not just from its Halloween season discovery, but from the ghostly way it haunts the edges of our cosmic backyard. With an orbit so elongated it takes 40,000 years to complete a single journey around the Sun, the Goblin should be just another curious frozen rock in the Kuiper belt. But this pint-sized world is hiding a secret one that might lead us to the greatest solar system discovery of our time, the fabled planet X. What makes the Goblin special isn't its size. It's barely 300 kilometers wide, but the peculiar path it follows. Like a cosmic detective's clue, its extreme orbit appears to have been sculpted by something massive lurking in the darkness. Along with a handful of other distant objects, the Goblin's trajectory suggests the gravitational influence of an unseen giant, perhaps 5 to 10 times Earth's mass, hiding in the frozen depths beyond Pluto. This isn't just speculation, the math backs it up. When astronomers plot the orbits of these far-flung worlds, their paths cluster in a way that's statistically impossible unless something huge is herding them like celestial sheep. The hunt for this elusive ninth planet has become one of astronomy's most gripping sagas. Telescopes around the world are scanning the skies, probing patches of darkness where calculations suggest Planet X might be hiding. The challenge, it's likely incredibly faint, reflecting almost no sunlight, and moving so slowly it barely stands out against the backdrop of stars. Finding it would be like spotting a single dim streetlight in a blizzard from halfway across the country. Yet the payoff could rewrite everything we know about our solar system's history. If Planet X exists, it wouldn't just be another world added to the list. Its sheer size and distant orbit imply a dramatic past. Perhaps it was flung outward during the solar system's chaotic infancy, or maybe it's an exiled wanderer captured from another star entirely. Some theorists even suggest its gravity could explain why the solar system's plane is slightly tilted, a mystery that's puzzled scientists for decades. Every new calculation, every fresh simulation brings us closer to understanding whether we're dealing with a real planet or a celestial phantom, a trick of incomplete data. The Goblin and its kin are more than just icy curiosities. They're breadcrumbs leading us toward what could be the last great discovery in our own cosmic neighborhood. Whether Planet X turns out to be a frozen super-Earth, a rogue interloper, or merely a statistical illusion, the search itself is forcing us to rethink how planetary systems form and evolve. One thing's certain, out in the darkness something is stirring, and the Goblin might just be the first whisper of its presence. On the sweltering night of August 15, 1977, an ordinary radio telescope in Ohio picked up something extraordinary. A 72-second burst of radio waves so powerful, so peculiar, that the astronomer who discovered it scrawled a single, stunned word in the margin of the data printout: "Wow." 4 decades later, that signal remains the most tantalizing and frustrating clue we've ever found in the search for extraterrestrial intelligence. Unlike cosmic static or human-made interference, the WOW signal had all the hallmarks of a deliberate transmission. A narrow frequency band matching the quietest part of the radio spectrum, precisely where alien civilizations might broadcast to be heard over the universe's noise. It was as if the cosmos had whispered hello, then vanished without another word. So what made this signal so special? The numbers tell part of the story. registering 30 times louder than background radiation at exactly 1420 MHz, the frequency of hydrogen, the most abundant element in the universe. The signal appeared to originate near the constellation Sagittarius. Its intensity rose and fell in a perfect curve, matching how a distant transmission would sweep across Earth's rotating telescope. But the real kicker: it hasn't been heard since, not once. Despite hundreds of follow-up scans and decades of searching, the WOW signal remains a one-off event, a cosmic flare that refuses to repeat. This enduring mystery has fueled endless debate. Could it have been a natural phenomenon? Some argue it might have been an unusually focused burst from a comet's hydrogen cloud, except no known comets were in the area at the time. Others suggest it was a glitch, a rogue reflection of human-made signals bouncing off space debris. But neither explanation fully accounts for the signal's precision or its eerie resemblance to what theorists predicted an alien beacon might look like. There's also the unsettling possibility that we caught the tail end of a one-time transmission, like overhearing a single word from a conversation light years away, never to hear the rest. The signal's ephemeral nature raises even deeper questions. If it was artificial, why hasn't it repeated? Civilizations advanced enough to broadcast interstellar messages would likely send them continuously or in predictable patterns. Unless, of course, they were deliberately sending short, targeted pulses, a cosmic "Are you there?" aimed at specific stars, or perhaps the signal was never meant for us at all. Imagine an alien relay station flickering on momentarily as it swept past our corner of the galaxy, its beam grazing Earth by pure chance. What makes the WOW signal so haunting isn't just its unanswered origin, it's the way it forces us to confront how ill-equipped we are to find answers. Our searches for extraterrestrial intelligence often assume alien civilizations will communicate in ways we can anticipate. But what if their technology, their motives, even their concept of communication are utterly foreign to us? The WOW signal could be a message in a bottle we lack the vocabulary to read, or a cosmic prank played by the universe itself. For now, it remains an indelible question mark in the sky, a 72-second enigma that proves sometimes the most profound mysteries aren't about what we find, but what slips through our fingers. And that's what keeps astronomers listening, scanning the static for another whisper that might finally break the silence. In the constellation Cygnus, nearly 1,500 light-years from Earth, a single star flickers like a candle in the wind. But this isn't the gentle twinkle of atmospheric distortion. KIC 8462852, better known as Tabby's star after the astronomer who first studied its bizarre behavior, dims in ways no natural phenomenon should. Picture a sun that occasionally loses up to 22% of its brightness, as if something colossal is drifting across its face, but not just anything. To block that much light would require an object 50 times wider than Earth, and unlike the predictable dips caused by orbiting planets, Tabby's star dims erratically, sometimes for days, sometimes for weeks, with no discernible rhythm. When the Kepler Space Telescope first spotted these anomalies in 2015, the astronomical community scrambled for explanations. The most tantalizing and controversial was the suggestion of an alien megastructure, a Dyson swarm, a hypothetical network of solar collectors built by an advanced civilization to harness the star's energy. The idea wasn't pure science fiction. Physicist Freeman Dyson had proposed such constructs decades earlier as a potential signature of intelligent life. And Tabby's star's irregular dimming pattern seemed to fit. Instead of the clean, symmetrical dips created by planets, its light curves were jagged, asymmetric, exactly what you'd expect if massive, uneven panels were orbiting the star in unpredictable configurations. But before we rewrite the history books, there are earthly explanations to consider. One leading theory points to vast clouds of dust, possibly from a shattered planet or a swarm of comets, drifting in front of the star. Dust could explain the irregular dimming. Different particle sizes would block light unevenly, and observations eventually detected infrared signals consistent with dust particles absorbing and re-emitting starlight. Yet even this explanation leaves gaps. The dust would need to replenish constantly to sustain the star's decades-long dimming trend, which raises the question, what cosmic event could produce so much debris for so long? Then there's the star's own behavior adding fuel to the fire. Unlike most suns, which brighten as they age, Tabby's star has been mysteriously fading over the past century, a fact uncovered by sifting through century-old photographic plates. This long-term dimming, combined with the sudden dips, suggests something far more complex than a mere dust cloud. Could it be internal stellar activity, like massive sunspots or magnetic storms? Possibly, but no known stellar physics produces effects this dramatic. What makes Tabby's star so compelling isn't just the unanswered questions, it's the way it forces us to confront the limits of our knowledge. Here's an object that defies every category we've created, sitting in plain sight. It's a reminder that the universe doesn't care about our expectations. Whether the answer turns out to be alien engineering, an unprecedented cosmic collision, or something entirely new, Tabby's star has already done something extraordinary. It's shown us how much wonder is left to uncover in the familiar glow of the night sky. Imagine the universe as a grand cathedral, its arches and buttresses hidden in shadow, only the glowing lamps of galaxies revealing where the structure stands. This unseen architecture, the dark matter halos enveloping every galaxy, is both the universe's greatest supporting act and its most frustrating enigma. We know it's there not because we can see it, but because without it, galaxies would fly apart like unspooled thread. Stars orbit their galactic centers so fast that the gravity of visible matter alone couldn't hold them. Something invisible must be anchoring them in place. That something is dark matter, and its halos are the ghostly skeletons upon which the cosmos builds its luminous flesh. These halos aren't just vague clouds, they're dynamic, sprawling structures that can stretch millions of light years beyond a galaxy's visible edge. Simulations show them as intricate webs, their gravitational tendrils guiding the birth and movement of galaxies like cosmic puppet strings. The Milky Way, for instance, resides within a halo that may weigh 30 times more than all its stars and gas combined. Yet for all their influence, dark matter halos refuse to reveal their true nature. They don't emit, absorb, or reflect light. They don't even collide with each other the way normal matter does. When galaxies merge, their dark halos pass through one another like phantoms, leaving the stars to tangled behind. Why does such a fundamental component of reality remain so elusive? Part of the challenge is that dark matter likely isn't made of atoms or any particles we've detected. It could be weakly interacting massive particles that barely touch ordinary matter except through gravity, or actions, hypothetical particles so lightweight they behave more like waves than discrete objects. Some theories even suggest primordial black holes, forged in the universe's first second, could be lurking invisibly within these halos. The frustrating truth is we've built detectors deep underground, launched telescopes into space, and smashed particles at near light speed, and still dark matter slips through our nets. But the real cosmic curveball comes when we look at small galaxies. According to our models, dark matter halos should have dense, cuspy centers, but many dwarf galaxies show cores that are mysteriously smooth, as if something has been scouring out their innards. This core cusp problem has led to radical ideas. Maybe dark matter can interact with itself through some unknown force, creating friction that flattens those central peaks. Or perhaps our understanding of gravity itself is incomplete, and what we call dark matter is really a sign that Einstein's equations need revising at galactic scales. The halo's fingerprints appear everywhere, in the way galaxies cluster like beads on a string, in the bending of light around galaxy clusters, even in the universe's large-scale structure. Yet the more we learn, the stranger dark matter seems. Some halos appear to be missing galaxies they should host, while others cradle galaxies far brighter than expected. It's as if the universe handed us the blueprints to its construction but left the key to the legend untranslated. What makes these halos so captivating isn't just their mystery, it's their inevitability. Every galaxy, every cluster, every thread of the cosmic web is woven around them. They're the silent partners in the universe's dance, felt but never seen. And until we crack their secrets, we're left with this humbling truth. Most of the cosmos isn't just unknown, it's invisible. At the heart of our galaxy, something lurks with the power to reshape life across the cosmos, not with a fiery explosion or a crushing gravitational pull, but with an invisible tsunami of pure energy. These are galactic superwaves, theorized cataclysms of cosmic rays erupting from the Milky Way's core in cycles so vast, they make ice ages feel like fleeting seasons. Picture a shockwave rippling outward at near light speed, carrying enough high-energy particles to bathe entire star systems in radiation capable of altering atmospheres, triggering mass extinctions and rewriting the fate of civilizations. And the most unsettling part, we may have already survived one. The theory hinges on the behavior of Sagittarius, a star, the supermassive black hole anchoring our galaxy. While it seems dormant now, evidence suggests it periodically awakens in violent bursts, not just feeding on nearby matter, but belching out jets of cosmic rays so intense they could reach Earth with devastating consequences. Geological records reveal eerie clues: layers of irradiated isotopes in ancient ice cores, sudden spikes in extinction events, and traces of interstellar dust unusually rich in rare elements, all time-stamped to roughly every 10 to 15 million years. It's as if the fossil record itself carries scars from these cosmic bombardments. But how could something so distant affect us so profoundly? Unlike supernova or asteroid impacts, a superwave's danger isn't just its initial blast, it's the aftermath. As the wave plows through interstellar space, it compresses gas and dust ahead of it, potentially triggering waves of star formation or even pushing comets from the Oort cloud into collision courses with inner planets. The radiation alone could shred Earth's protective ozone layer for centuries, exposing life to deadly ultraviolet levels while showering the surface with muon subatomic particles capable of penetrating deep underground, turning even the safest shelters into death traps. The smoking gun might lie in a controversial but compelling study of lunar soil. Apollo mission samples revealed strange concentrations of radioactive iron-60, an isotope typically forged in supernova or black hole eruptions, and it aligns suspiciously well with a minor extinction event 2.6 million years ago. If confirmed, this could mean our ancestors weathered a glancing blow from a superwave's outer edges, a mere whisper of its full destructive potential. What makes this theory so gripping isn't just the past, it's the future. If superwaves are cyclical, when's the next one due? Calculations vary, but some models suggest we're entering a window of heightened risk. The good news, we'd likely have centuries of warning as the wave's leading edge visible through gamma-ray telescopes crept across the galaxy. The bad news, there's no guarantee we'd recognize the threat in time, or that we could do anything to shield ourselves from a force capable of sterilizing entire star systems. Yet amidst the doom scenarios, there's a tantalizing silver lining. Superwaves might be cosmic gardeners as much as destroyers. By compressing interstellar clouds, they could seed new stellar nurseries, and their radiation might even spark the chemical reactions that give rise to life's building blocks. It's a reminder that the universe's most violent forces are often its most creative, a duality written into the fabric of reality itself. The question isn't just whether we'll face another superwave, but whether we'll recognize it as catastrophe or catalyst when it arrives. At the center of the Virgo cluster, a celestial titan feasts in the darkness, Messier 87, a galaxy so massive it bends the rules of cosmic evolution. This isn't just any galaxy, it's a cosmic cannibal stretching over 120,000 light-years and weighing in at nearly 3 trillion times the mass of our Sun. But what truly sets Messier 87 apart isn't its size, it's the way it grows. Unlike most galaxies that form stars from gas, this behemoth expands by devouring its neighbors, swallowing entire galaxies whole like a spider ensnaring flies in its web. The evidence is written in the star's streams of stellar debris winding like ribbons through Messier 87's outer reaches, the carcasses of galaxies it's absorbed over billions of years. These aren't quiet mergers, they're violent events that rip stars from their orbits and fling them into chaotic new paths. Yet somehow, Messier 87 remains eerily stable, its smooth elliptical shape undisturbed by the chaos within. This defiance of expectations has forced astronomers to reconsider how giant galaxies evolve. Traditional models suggest such colossal structures should take far longer to form than the age of the universe allows. But Messier 87's appetite provides a shortcut growth through conquest, not just creation. Then there's the monster at its heart, the first black hole ever photographed, a supermassive Goliath weighing 7 billion solar masses. This black hole isn't just a passive vacuum, it's an engine of destruction and creation, launching a jet of plasma nearly 5,000 light-years into space at 99% the speed of light. The physics behind this jet is mind-bending. Particles within it don't just move fast, they're accelerated by magnetic fields twisted into knots by the black hole's spin, creating a cosmic particle cannon that outshines the galaxy itself. What makes this jet so extraordinary is how it challenges Einstein's theory of relativity in action. At such speeds, time dilates, clocks on the jet's particles would tick infinitely slowly from our perspective. The jet also bends light around it like a lens, offering a real-world lab for studying gravity's warping effects. Yet for all its power, the jet raises a perplexing question. Why does it shoot out in just one direction? Most theories predict symmetrical outflows, but Messier 87's jet is lopsided, suggesting the black hole's accretion disk might be wobbling like a spinning top nearing its end. Even more intriguing is the black hole's role in the galaxy's feeding frenzy. Some astronomers suspect its gravitational might acts like a cosmic blender, shredding incoming galaxies before they're digested, their stars redistributed in a process that's more orderly than random. This could explain why Messier 87 remains so smooth despite its violent history, a paradox that's reshaping our understanding of galactic ecology. The story of Messier 87 isn't just about one galaxy's dominance, it's a preview of our own future. In billions of years, the Milky Way and Andromeda will merge, potentially forming a similar elliptical giant. By studying this cosmic cannibal, we're glimpsing the fate of galaxies on the grandest scale and the invisible forces that shape them. It's a reminder that in the universe, growth often comes not from building, but from the relentless pull of gravity's embrace. In the constellation Serpens, some 4,000 light-years away, spins a world unlike any other Pulsar J1719-1438b, a planet so bizarre it gleams like a cosmic jewel. This isn't just another exoplanet, it's a celestial diamond, a chunk of crystallized carbon orbiting a pulsar so dense, a teaspoon of its material would weigh billions of tons on Earth. But how does a planet made of diamond even form? The answer lies in a cosmic demolition derby of apocalyptic proportions. This planet's story begins with a star much larger than our Sun, one that lived fast and died violently. When it exhausted its nuclear fuel, it collapsed in a supernova explosion, leaving behind a spinning stellar corpse, a pulsar. But before this star died, it likely had a companion, a white dwarf star made mostly of carbon and oxygen. As the supernova's shockwave ripped through space, the white dwarf was stripped down to its core, its outer layers blown away. What remained was a naked, ultra-dense remnant, a planet-sized diamond forged in the crucible of stellar catastrophe. The numbers behind this world are staggering. Despite being only about 37,000 miles wide, roughly 5 times the diameter of Earth, it packs a mass greater than Jupiter, making it one of the densest objects ever discovered. That density suggests it's not just sprinkled with carbon. It's likely a solid crystalline lattice, a diamond in the rough on a planetary scale. Imagine a mountain range where the peaks aren't rock but faceted gemstones stretching into space. Yet the real puzzle isn't just what it's made of, it's how it survived at all. Pulsars are notorious for their lethal radiation, blasting nearby space with enough X-rays and gamma rays to vaporize most planets. For this diamond world to endure, it must have migrated into its current orbit after the supernova, or perhaps it was hardened enough by the explosion itself to withstand the pulsar's fury. Either scenario turns conventional planet formation theories on their head. Astronomers suspect the planet's composition might also explain its bizarre orbit. Circling its pulsar every 2 hours and 10 minutes at a distance less than that between Earth and the Moon, it's locked in a gravitational dance so tight, the pulsar's radiation should be slowly evaporating it. Yet the diamond structure's incredible strength might be resisting this disintegration, creating a cosmic standoff between destruction and durability. What makes this world more than just a celestial curiosity is what it teaches us about the universe's creativity. Planets don't just form in quiet disks of gas and dust, they can be born from chaos, shaped by violence, and emerge as something utterly unexpected. PSR J1719-1438b isn't just a diamond in the sky. It's a reminder that the cosmos specializes in turning catastrophe into wonder. And somewhere out there, in the infinite dark, other impossible worlds are waiting to be found. Hovering over Saturn's north pole like a colossal piece of celestial geometry, the planet's hexagonal storm is one of the solar system's most mesmerizing puzzles. This 6-sided jet stream, stretching 25,000 miles across wide enough to fit 4 Earths side by side, has churned relentlessly for at least 4 decades, possibly far longer. Unlike the chaotic swirls of Jupiter's Great Red Spot or the fleeting storms on Neptune, Saturn's hexagon is eerily precise, its razor-sharp edges defying everything we know about atmospheric turbulence. How can a planet's weather system produce something so symmetrical, so stubbornly geometric, in a universe that favors asymmetry and chaos? The answer might lie in the dance of fluid dynamics. On Earth, similar patterns emerge in lab experiments when fluids of different densities rotate at high speeds, an effect known as the Kelvin-Helmholtz instability. Picture a spinning bucket of water. Under the right conditions, the fluid can form stable polygons. Some scientists suggest Saturn's hexagon operates on the same principle, just scaled up to planetary proportions. The planet's rapid rotation a day lasts just 10.5 hours. Combined with the layered flow of its atmosphere, could generate standing waves that lock the storm into this angular shape. It's as if the universe ran a physics simulation with perfect parameters and left it running on loop. Yet this explanation raises another question: why don't other gas giants have hexagonal storms? Jupiter's polar vortices are chaotic spirals. Uranus sports a wobbly, irregular polar cap. Saturn's uniqueness might come down to 2 factors: depth and composition. Unlike Jupiter's turbulent, shallow weather layers, Saturn's atmosphere is deeper and more stratified, allowing stable wave patterns to propagate upward. Furthermore, the planet's lower internal heat compared to Jupiter could mean less thermal disruption, letting the hexagon maintain its shape for centuries. The hexagon's persistence is even more baffling when you peer inside it. Infrared images reveal a towering central vortex, a colossal hurricane-like storm rising 30 miles above the surrounding clouds, with winds screaming at 320 miles per hour, twice the speed of Earth's strongest hurricanes. And somehow, this maelstrom doesn't disrupt the hexagon's pristine walls. It's like a whirlpool spinning inside a glass jar without ever cracking the sides. Perhaps the most haunting possibility is that we're witnessing something transient, a cosmic coincidence that won't last. Ground-based telescopes first spotted hints of the hexagon in the 1980s, but Cassini's close-up views confirmed its stability. Yet without continuous monitoring, we can't know if this is a fleeting phenomenon or a permanent fixture of Saturn's climate. If it were to vanish tomorrow, we'd be left wondering whether we'd imagined it, or whether the universe had briefly peeled back a corner of its rulebook to show us something impossible. The hexagon isn't just a weather pattern, it's a lesson in humility. For all our advances in planetary science, Saturn's North Pole remains a blackboard scribbled with equations we're still learning to solve. With every observation, we're reminded that even in our own cosmic backyard, nature reserves the right to surprise us, and that the most profound mysteries often wear the simplest shapes. In October 2017, astronomers spotted something streaking through our solar system that shattered every expectation, an object so strange it sparked one of the greatest cosmic debates of our time. This was Oumuamua, the first known visitor from interstellar space. At first glance, it appeared to be just another asteroid tumbling silently past the Sun. But as scientists tracked its path, they realized this was no ordinary rock. Oumuamua was accelerating, not just from gravity's pull, but as if some unseen force were pushing it forward, an impossibility for inert celestial bodies. The mystery deepened when telescopes tried to pin down its shape. Instead of the typical lumpy asteroid profile, Oumuamua reflected light in erratic bursts, suggesting an elongated, possibly cigar-like form stretching hundreds of meters long. Even stranger, it showed no signs of outgassing the telltale jets of dust and ice that comets produce when warmed by the Sun. Normally, such jets explain unexpected acceleration, but Oumuamua left no visible trail. It moved as if propelled by something invisible, a cosmic sail catching an unfelt wind. Theories exploded as researchers scrambled to explain these anomalies. One camp insisted it was an exotic comet, its outgassing so subtle our instruments missed it. Others proposed something far wilder. Oumuamua could be a hydrogen iceberg, a chunk of frozen molecular hydrogen slowly evaporating in sunlight, leaving no visible trace. But the most provocative idea came from Harvard astrophysicist Avi Loeb, who suggested it might be artificial, a discarded light sail from an alien civilization drifting between the stars. Critics dismissed the light sail hypothesis, pointing out natural explanations were more plausible. Yet even the hydrogen iceberg theory had holes. Such objects shouldn't survive the journey between stars without evaporating entirely. The comet explanation, while conservative, struggled to account for the complete absence of a dust tail or gas emissions. Every proposed solution raised new questions, turning Oumuamua into a Rorschach test for astronomers. What you saw in its behavior often said more about your assumptions than the object itself. What makes Oumuamua so endlessly fascinating isn't just its oddities. It's the tantalizing possibility that we might have glimpsed something unprecedented. Future telescopes could reveal more interstellar visitors, offering fresh clues. Until then, this enigmatic traveler remains a cosmic cipher, challenging us to wonder whether we witnessed a quirk of nature or something far more extraordinary. Hidden in the constellation Coma Berenices, floating like a phantom in the sea of stars, lies a galaxy that shouldn't be, or at least one that defies everything we thought galaxies were supposed to be. This is Dragonfly 44, a cosmic paradox so faint, it was only discovered in 2015 after astronomers combined dozens of telescope images to tease its ghostly silhouette from the darkness. At first glance, it seems unremarkable, a smudge of light barely 1% as luminous as the Milky Way. But peer closer and the truth emerges. This whisper of a galaxy weighs as much as our own, yet emits almost no light. The reason, Dragonfly 44 isn't just sprinkled with dark matter, it's drenched in it. A celestial shadow where the unseen outweighs the visible by a staggering 10,000 to 1. The existence of this dark galaxy flips our understanding of star formation on its head. Normally, galaxies are factories of light, their gas collapsing into stars under gravity's pull. But Dragonfly 44 is a cosmic desert with so few stars spread so thinly. It's like finding a single candle flickering in a football stadium. Yet its outer stars orbit at speeds that betray an immense gravitational grip, one that can only be explained if an invisible scaffold of dark matter holds the galaxy together. Picture a spiderweb with dew droplets scattered miles apart. The water barely weighs anything, but the silk strands binding them are strong enough to catch birds. That's Dragonfly 44's secret. Its dark matter web is the true structure, with stars as accidental ornaments. How does something like this form? One theory suggests it's a failed galaxy, a place where dark matter clumped as usual, but gas never cooled enough to birth stars in large numbers. Another idea posits it was once normal, until violent encounters with other galaxies stripped away its gas and stars, leaving behind a dark matter skeleton. There's even a tantalizing possibility that Dragonfly 44 isn't alone, that the cosmos is littered with such shadowy giants, undetectable by conventional surveys. The implications are profound. If galaxies can exist with almost no stars, our census of the universe might be missing an entire population of cosmic phantoms. Worse, their presence could undermine our best methods for mapping dark matter, which often rely on tracing its influence on luminous matter. Dragonfly 44 doesn't just challenge our ideas about galaxies, it forces us to question whether we've been seeing the universe through a keyhole, oblivious to the shadows moving just beyond the light. Yet for all its mystery, this dark galaxy might hold clues to one of cosmology's deepest puzzles: the nature of dark matter itself. Unlike typical galaxies where stars and gas complicate the picture, Dragonfly 44's extreme simplicity offers a pristine lab to study dark matter's behavior. Are its particles cold, moving sluggishly as most models assume? Or could their properties be stranger, explaining why this galaxy's dark halo is so unusually smooth? Dragonfly 44 is more than a curiosity, it's a cosmic mirror, reflecting how much we still don't understand about the universe's hidden architecture. In a cosmos where light dominates our perception, this dark galaxy whispers a humbling truth: what we see may only be the faintest echo of what's really out there. Tucked away in the constellation Monoceros, the celestial unicorn, lurks one of the strangest objects ever discovered. The unicorn, a black hole so small it defies classification. At just 3 times the mass of our Sun, this cosmic oddball straddles the razor's edge between impossibility and revelation, blurring the line between neutron stars and black holes. It's a cosmic Goldilocks, too dense to be a neutron star, yet so lightweight it challenges our understanding of how black holes form. What makes the unicorn truly remarkable is how we found it. Unlike its supermassive cousins that reveal themselves by tearing stars apart or spewing jets of plasma, this tiny phantom betrayed its presence through the subtlest of clues: the gentle wobble of a red giant star orbiting something unseen. By tracking the star's rhythmic velocity changes, astronomers realized it was dancing with a companion roughly 3 solar masses, emitting no light of its own. The math left only one plausible explanation: a black hole smaller than any previously confirmed. This discovery throws a wrench into astrophysics' most fundamental models. According to conventional wisdom, when massive stars die, they leave behind either a neutron star, a city-sized ball of degenerate matter so dense a sugar cube-sized piece would weigh 1 billion tons, or, if heavy enough, a black hole. The dividing line between these fates was thought to be around 5 solar masses. Below that, gravity alone couldn't crush a neutron star further. The unicorn, defying expectations, suggests black holes might form at masses so low they overlap with the heaviest neutron stars, creating a mass gap where the universe's rulebook seems to rewrite itself. Theories abound to explain this cosmic exception. Perhaps the unicorn was born from the merger of two neutron stars, their combined mass tipping the scales just enough to collapse into a black hole. Alternatively, it could be a primordial black hole, forged in the universe's chaotic infancy rather than from a dying star, the most intriguing possibility. It might represent an entirely new class of light black holes lurking invisibly throughout the galaxy. If true, thousands could be hiding in plain sight, their subtle gravitational tugs the only hint of their existence. Yet the unicorn's most tantalizing property isn't just its size, it's how it consumes matter. Unlike larger black holes that rip gas from companion stars in violent, X-ray bright feasts, the unicorn's petite event horizon allows only a trickle of material to spiral inward. This gentle accretion produces no dramatic flares, making it nearly undetectable by traditional methods. It's a cosmic sip where others gulp, a whisper in a universe of screams. For astronomers, this changes the game. If lightweight black holes are common, they could solve persistent mysteries like the origin of certain gravitational wave signals or the unseen, dark component of stellar mass in our galaxy. They might even serve as laboratories for testing quantum gravity, their tiny event horizons offering glimpses of how space-time behaves under extremes that dwarf even the crushing density of neutron stars. The unicorn doesn't just fill a gap in our catalogues, it forces us to reconsider how black holes are born, how they grow, and where the boundaries of cosmic reality truly lie. In a universe where the most dramatic phenomena often dominate our attention, this quiet outlier reminds us that sometimes the smallest discoveries cast the longest shadows. What else might be hiding in the dark, waiting to rewrite the rules we thought we knew? In the violent ballet of stellar death, where stars typically meet their end in a blaze of self-destruction, there exists a bizarre anomaly: stars that cheat death. These cosmic survivors, nicknamed zombie stars, emerge from supernova explosions not as lifeless remnants, but as battered, half-destroyed versions of their former selves. The most puzzling of these are the Type IX supernova, stellar explosions powerful enough to rip a star apart, but not quite powerful enough to finish the job. Picture a white dwarf, the dense, Earth-sized core of a dead star locked in a fatal dance with a companion star. As it siphons material from its neighbor, the white dwarf grows unstable, eventually reaching a critical mass that triggers a thermonuclear explosion. In a typical Type Ia supernova, this detonation would annihilate the white dwarf completely, leaving behind nothing but an expanding cloud of debris. But Type IX events are different. These are the cosmic equivalent of a dud firework explosions that fizzle partway through, ejecting just a fraction of the star's material while leaving a scarred but intact core behind. What causes this stellar hesitation? The leading theory suggests these explosions might begin deep within the white dwarf, where the nuclear flame front struggles to propagate evenly. Instead of a symmetrical detonation that obliterates the entire star, the flame sputters, creating an asymmetric blast that blows off the star's outer layers while leaving its dense interior remarkably intact. Imagine lighting a stick of dynamite that only partially explodes. The outer casing is shredded, but enough of the core remains to reassemble into something new. The aftermath is even stranger. Some zombie stars appear to recoil from their own explosions, hurtling through space at extraordinary speeds while trailing streams of ejected material like cosmic bloodstains. Others pulsate erratically, their surviving cores flickering with the trauma of their incomplete demise. The most extreme survivors might even reignite nuclear fusion in their remaining material, temporarily returning to life as bizarre hybrid stars, part white dwarf, part newborn stellar phoenix. These zombie stars aren't just celestial oddities, they're cosmic laboratories. By studying them, astronomers can probe the precise conditions needed to trigger supernova, fine-tuning our understanding of stellar physics. They also offer clues about the nature of dark energy, since standard type Ia supernovae serve as standard candles for measuring cosmic distances. If some of those historical supernovae were actually failed IAX events, it could mean recalculating the expansion rate of the universe itself. Perhaps the most tantalizing question is how common these survivors might be. For every zombie star we've spotted, there could be dozens more lurking undetected, their faint glow lost in the glare of younger, healthier stars. Each one carries a story written in shockwaves and scars, a story that challenges our assumptions about how stars live, die, and sometimes refuse to go quietly into the cosmic night. Deep in the spaces between galaxies, where telescopes usually find only darkness, lies one of cosmology's most embarrassing secrets. Half the universe's normal matter is missing. Not dark matter, the mysterious, invisible stuff that outweighs ordinary atoms 5 to 1, but the very protons, neutrons, and electrons that make up stars, planets, and us. This is the case of the missing baryons, and the culprit might be hiding in plain sight, woven into the universe's largest structure, the cosmic web. Picture the universe as a sponge, its holes representing vast cosmic voids while its strands form an intricate lattice of gas filaments thinner than a single human hair stretched across a football field. These faint threads, predicted by simulations but nearly invisible to our instruments, could contain up to 50% of all normal matter, stored not in dazzling galaxies or glowing nebulae, but in diffuse clouds of million-degree gas called WIM, the warm-hot intergalactic medium. The challenge, spotting something so tenuous it barely leaves a fingerprint on the cosmos. For decades, astronomers tallied up all the observable baryons in stars, galaxies, and gas clouds, only to find they accounted for barely half the amount predicted by the Big Bang's chemical recipe. The rest seemed to vanish without a trace. Then came a breakthrough. By studying distortions in the cosmic microwave background light left over from the universe's infancy, researchers realized the missing atoms weren't truly gone. They'd been hiding in those nearly invisible filaments, heated to temperatures so extreme they emit X-rays too faint to detect directly. Hunting these phantom baryons requires telescopes with the patience of cosmic detectives. Instruments like the European Space Agency's XMM Newton and NASA's Chandra X-ray Observatory have begun spotting hints of the WIM by observing distant quasars, the brilliant cores of active galaxies whose light passes through these filaments on its way to Earth. Like a flashlight beam shining through fog, the gas absorbs specific X-ray wavelengths, leaving behind spectral barcodes that reveal its composition and temperature. Another clever trick involves studying the Sunyaev-Zeldovich effect, where cosmic web gas subtly distorts the CMB as it travels through space, like heat ripples distorting a desert mirage. Yet even these methods only glimpse fragments of the web. The real revolution may come with next-generation observatories like ESA's Athena mission, set to launch in the 2030s with X-ray vision sharp enough to map these filaments in 3D. There's also hope that radio telescopes could detect the WIM faint hydrogen signatures using techniques similar to medical MRI scans, peeling back layers of the universe's anatomy one wavelength at a time. What makes this search so crucial isn't just balancing the cosmic ledger. These filaments are the universe's circulatory system, funneling gas into galaxies to fuel new stars and planets. They might also hold clues to why galaxies form where they do, or how dark matter's gravity sculpts the web's architecture. Solving the baryon mystery isn't about finding missing matter. It's about completing our map of reality's scaffolding. And somewhere in those ghostly strands, the universe's most fundamental ingredients are waiting to be found. From the Great Attractor's unseen pull to the ghostly whispers of the WOW signal, these 25 cosmic enigmas aren't just curiosities. They're the universe's way of nudging us out of our complacency. Each one is a crack in the facade of our understanding, a reminder that for every question we answer, the cosmos fires back with 10 more. Think about it. We live in a reality where black holes can weigh less than a star yet warp spacetime just as fiercely, where galaxies can hide in darkness while outweighing our Milky Way, and where entire planets might be forged from diamond in the heart of stellar chaos. These aren't plot twists from science fiction. They're real, documented phenomena that defy textbooks and force scientists back to the drawing board. What's truly humbling isn't just the scale of these mysteries, it's how recent most of these discoveries are. A century ago, we didn't even know other galaxies existed. Now we're mapping structures so vast they challenge the fundamental principle that the universe should look uniform everywhere, and just imagine what we might uncover next. Will the James Webb Telescope spot more dark galaxies like Dragonfly 44? Could gravitational wave detectors reveal echoes of colliding universes in the cold spot? Or will some backyard astronomer scanning the skies with a modest telescope stumble upon the next Oumuamua, another interstellar visitor carrying secrets from the void? This is why space exploration matters. It's not just about filling in gaps on a map, it's about confronting the sheer weirdness of reality. Every time we peel back a layer of the cosmos, we're met with phenomena that stretch our definitions of what's possible. And that's the thrill of it. The universe isn't a static museum exhibit. It's a living, evolving puzzle where the pieces keep changing shape. So tell us, which of these cosmic riddles keeps you up at night? Is it the Fermi Bubbles towering over our galaxy like silent sentinels of an ancient cataclysm? Or the Boots Void, that eerie cosmic desert where galaxies fear to tread? Drop your thoughts in the comments, and if you're craving more deep dives into the universe's greatest mysteries, hit subscribe. Because one thing's certain, this story is far from over, and the next chapter promises to be even stranger. After all, the universe doesn't owe us answers. But it does offer endless wonders for those willing to look up and wonder.